Hi and welcome back. This is Andre and today we discuss a paper that's going to be published at NeurIPS 2021. It's a very interesting paper that introducing a new type of model which aims to be a sort of non-parametric version of a deep learning model. It's not actually non-parametric, but it's still, I would say, an interesting idea. So I decided to give it a read and do a review of it. And it seems that the authors are from Oxford University, and they are Yannick Kossen, Neil Band, Claire Lille, Aidan Gomez, Tom Reinforth, and Yarin Gal. And it's a cool idea that they want to use self-attention between data points. Let's see what they are saying. So they are saying that they introduce a model called a non-parametric transformer. It's actually not a non-parametric model, like it has plenty of parameters in it, but it wants to use the idea of a non-parametric, meaning that you use the data points to predict. So in standard deep learning and in just standard supervised learning, you obtain an input and the input has some features and you are using a model, let's say M, and you are making a prediction, for example, a classification. So in standard deep learning, all the inputs to the model are just the features of one input. So the prediction is P of Y given X. Now, what they want to introduce here, they want to introduce a type of model which can predict let's say a classification based on the input as well as the whole data set, right? So let's make it clear that these are the inputs for the prediction and this is the let's say data that you have. And this is your input and this is the classification that you have. So this model doesn't get as input only the features of one input, but it also gets as input the whole data set that you have at your disposal. And it's an interesting idea because this part of, let's say, conditioning on the data, this is what they want to call a non-parametric approach. Because the output is a sort of a function of also of the other points. Again, it's a bit misleading that this is a non-parametric model because it's just not. Like a fully non-parametric model would be, for example, KNN, in which you have a bunch of data points and the prediction is based on the neighborhood of like what's the closest. So there you have maybe, let's say, a hyperparameter. While here you are going to have transformers and attention heads and a lot of MLP, so it's not actually non-parametric. Now, what's the idea that they are proposing? So this is your input data, and it's just a matrix where you have the data points and you have the attributes. And one clear point to mention is that with this model, you do not need, as I understand, you don't need a training as and the validation data set. You just train with the whole data set that you have, and then at test time, you can sort of append another data point and then make a prediction. This is similar with, let's say, other non-parametric approaches. For example, in Gaussian processing, you do not actually have a validation set. So, again, this is the input data, and they are creating, let's say, a way to use, in a way, self-supervised learning with supervised learning, combining them and train everything. So if this is your data, then the last column, they are saying that this is where you are putting the features. So technically, this is where you put the label. So for example, if it's a regression, there you put, let's say, the target, and if it's a classification, there you put the class. Of course, you do one hot encoding, but that's where you have the label, and all of those things, these are the features. Now, during training, we are going to, let's say, drop out some of those things stochastically. And then we want the model to train it to predict those things. So they got inspiration from, let's say, how all those transformers and how the NLPs, how BERT is essentially pre-trained, in which you take, so in BERT, you are taking, for example, a phrase, which is this one. You are stochastically dropping some of those things and then using the context you want to predict what's in the middle. They are doing the same thing. They are, let's say, dropping something stochastically, and they are using, in this case, everything around in order to predict it. So in BERT, it's just the things in the same phrase. They are extending it one level further and use also the, nearby points to do that. We're going to see exactly how. But that's the whole point. So at every training iteration, they are stochastically dropping some of them, and then, enforcing the model to predict those things in a very, let's say, simple to implement and actually interesting way. So I want to just remind what's attention, because it's heavily used in this thing. So what is this multi-head self-attention? The key point of multi-head self-attention is that you are having a matrix, which is, let's say, N and H, and the output is also a matrix that is of the same size. So the size does not change. Now, what's this multi-head self-attention? So I'm sort of expecting that you know what's the attention mechanism, so I'm going to just briefly review it. So here you have, let's say, n data points, and each of them is going to have an embedding of size h. Now, I will take those things, and just for simplicity, I will assume that I'm putting them like this. So we have n data points, and I sort of assume that the embedding is h equal with 1. Now, we are using something on attention. So we have some keys, we have some values, and we have, keys, values, and a query. In self-attention, all of them are the same thing. So the whole point is that we are taking these inputs, and for every sort of data point, you are, in a way, looking how similar are all the other data points. You are obtaining, let's say, a dot product between them. Then you are applying a softmax over that thing. And then you can take a linear combination of that thing. So for example, for this input, you could say that, hey, I'm attaining, let's say, 0.5, 0.1, 0.1. That's U0, that's U0, and this is U0.3. So now, at the output for this specific thing, it's going to be 0.5 times this value, 0.1 times the other value, 0.1 times the other value, 0 times the other value, and so on. So this self-attention mechanism, it's essentially taking, let's say, a vector, but it's a matrix, and outputting, let's say, combined versions of these elements. And you are doing this with something called multiple heads. So each head is going to look for some specific type of features. So at the end, you are getting higher and higher level features by just combining what's inside them. So here we combine everything. For this data point, we combine as well everything. For this data point as well everything. And if you apply this thing multiple times, at the end you get out some super high level features that are a combination, like multiple times combining the initial inputs. But the key point is that it is combining the rows of this matrix. So this is self-attention. Now, how is it actually used? So we discussed that their model has an input, an input matrix where some of them are stochastically masked. So meaning their values is made 0. Now they are using a linear embedding, which means that they are taking the value of each of these and they multiply it with just one matrix operation to get depth into the volume. Now I looked over the code base and I was curious, why did they make this thing? And it's very interesting. I mean, super simple, the answer. My let's say idea is that they are using this in order to enable using this sort of framework with regression and classification, with inputs that are both continuous as well as categorical. Because if you have, let's say, a value 0.5, you don't need to do anything. But if it is a categorical value, you one hot encode. So this is going to be 1, this is going to be 0. And like, what are you going to do? Because let's say here you have a continuous, here you have again a continuous value. So things are going to get mixed in a bad way. So what they are doing is they say, hey, we provide you a general framework in which you can have your matrix, as it is. We create embeddings for everything. So for continuous value, it is just going to get projected into, sort of this value times a vector. But for this categorical values, they are going to be mapped to, let's say, only one embedding of what's that thing, because this vector is going to be multiplied by a matrix. So you are going to have a matrix, let's say times 1, 0, and this is essentially selecting only one column. So here you'll have an embedding, which sort of wants to learn what's the combination for this thing. So again, they are making this, split to use embeddings, I believe, for the simplicity of handling both continuous and categorical values. And also I saw in the appendix that this is of size 64, sometimes 128, so it's quite a big embedding. It might have other reason, but surely one of them is that one to be simplified. So we do this thing once. So now we have n data points, each of dimension e, and now we also have an embedding of size e. And this algorithm, the whole point that it does is it is iteratively doing 2 steps. So there are 2 steps that are done iteratively. The first one is to use attention between data points and then attention between attributes. What does attention between data points means? It means that in a way we flatten this thing. So you see, we are taking the embedding size and we put them one near the other one on the right side. So sort of this would be one layer, one layer, one layer. And now we just apply self-attention between data points. So self-attention between data points is literally just what we discussed here, in the sense that we have the matrix and we sort of shuffle and combine the rows into higher level features. So now each sort of data point, the embedding for a data point will be just a combination of all the other data points. So we combine the data points. So now a data point is, let's say, a mixture of all the other data points. And after we do that once, then we combine the features individually for one data point. So for every single data point, we apply attention between the sort of feature embeddings. So if you look at one data point from, let's say, above, this is also a matrix. This is a matrix of size D times E. So you have D features, each of them with an embedding of size E. Now, again, you apply self-attention on the rows because you sort of want to create higher level features from those things. So and the output is also a thing of size DE. So at one step you combine data points, at the other step you combine features, and then you combine data points again and then features, data points, features, data point, features. And so at the end, all this matrix is in a way combined by itself. So it's all the data points interact with all the other data points and with the features of themselves. So things are in a way mixing around, and by mixing stuff around, you will get, for every position, you will get one type of an embedding. So even if you put here, because when you stochastically mask something, you are going to put a 0. You put 0 and then you apply this embedding, and then you will have at all those positions 0, 0, 0. After you mix this algorithm, so you apply step C and D like 10 times, then here you will have some value. So an embedding, let's say is 1, 0 0.5, 0 0.3, and 5. So now we got an embedding, and then we can project back into that thing by just applying one matrix multiplication. So we get from this thing, we apply a matrix multiplication. We apply then step C plus D, like, maybe 100 times. And then we get to an embedding, and then we are able to project back to what we have. And if it was a regression, then we are happy because we get one value. If it was a categorical value, then let's say we will get something like a 0.3 and then a 7, and we can just apply softmax over this and get the categorical value. So this algorithm is essentially a way to fill, missing entries. Like, these algorithms could easily be used to fill missing entries in a matrix. So instead of doing, let's say, mean imputation, you can just use this thing to fill inputs. And what's interesting is that they are treating labels, because the last column are the labels, as just, a feature. And you are essentially learning how to input those features. Simple idea. But what's in a way good about it is that during the optimization, the loss is somehow supervised and somehow unsupervised. So we discussed that we want to make a prediction of this form, where this represents inputs that are observed. So this means that, this represents, we want to predict the masked inputs. So we will have a matrix, let's say 5, 7, 2, 9. We mask some of them. So let's say we mask those things, which means that the inputs are becoming 0. And those masked, we want to predict the masked ones from the non-masked ones, meaning the observed ones. And they are proposing to use different probabilities for stochastically masking the features and stochastically masking the targets. I checked the appendix, and the masking, let's say, procedure is that you are selecting 15% of the data points, and then you pick 90% of the features, like you randomly pick 90% and you do, let's say, masking, and then you pick the other 10% of the features and you do something like a random perturbation. So if it was a continuous values, I think they were taking it from a normal distribution, so sort of basically put like random noise. And if it was categorical value, they were just shuffling the stuff. So they were essentially randomizing some stuff. But at the end of the day, at every epoch, 70%, no, 1/7, so 15% of the data points are essentially completely broken, completely destroyed. They are randomly chosen. And then the task of the algorithm is to predict those 15%. It's also interesting because, you know, when you do, let's say, standard train validation test sets, you are keeping, let's say, a validation of 15%, sort of. But here, they are able to use also the validation during training. So they are, at every epoch, they are creating a new validation test, and they are training to reconstruct that one, which is honestly is very similar to meta training, to the episodes, where you are creating, let's say, a new train validation set at every episode. You train to make that well, and then you pick another sort of those learning tasks and continue. And they are getting a loss from the targets, which is just log likelihood. So it's essentially, you know, cross entropy if you have a classification, or mean squared error if you have a regression task and you assume Gaussian noise. And they are also having a loss for the features. It depends what it is. You can assume it's the same types of loss, and then you have a hyperparameter between them. I looked into the appendix, and it's very interesting how they schedule this thing. So they're using a scheduler where, let's say, so this is as the time goes, and this is, let's say, lambda. And they start with a lambda from 1, and they go, let's say, to 0, which means that at the beginning, the algorithm is incentivized to care only about reconstructing the features well. And then as this moves on, it cares about predicting the targets well as well. Because at the end of the day, this algorithm is made to predict targets, not just do imputation. So this is how we train. Again, the interesting point is that it has a self-supervised thing into it. So it sort of gets more signal by using existing features into it. And they're saying somewhere that they observe that this, in a way, regularization, yes. They find that this sort of more supervision, meaning this self-supervision L features, have a beneficial regularization effect. Now, let's look over some experiments of how it performs, and then I'm going to tell you some of my thoughts about this thing. So these tables show the average rank across some methods. So they picked a bunch of data sets, like lots of them, and they hyperparameter tuned very well those, because I checked the code. And generally, this type of model performs, let's say, better, or most, best. Like if you rank across all those data sets, it generally performs best. This is for regression, this is for classification, and this was for some regression as well. No, sorry, this was binary classification as well, and this was regression. The key point is that it performs generally well. And now, so quantitatively, it's good. Now, qualitatively, they looked whether this model actually does what they intended to do. So they started with a synthetic task in which they want to check whether this model actually is able to look at different data points. So they created, honestly, a very simple experiment in which, so they create a very simple data set in which they are taking some data points. They duplicate the data points, so those features are literally identical. Now, for one of these data sets, they keep the features, And for the other one, you make the labels. And for the other one, you make the labels essentially 0. So sort of you mask them all the time. And you train this algorithm, and then the algorithm is going to find out to look like a lookup table, to look at the exact data point, because it sort of knows that it has a duplicate, and at test time, it learns to look at the most similar data point and sort of grab this value and put it there. So this is the attention matrix. So for this data, for those predictions, it learns to grab it from this one. So sort of the algorithm learns a lookup table to look at the most similar example. Another interesting thing is that, so this is a very synthetic data set, very simple. It just shows that it's able to learn to use other data points. Here they checked whether it actually learns to use the data points on real data. And honestly, I think it's mostly not. Because if you look at this table, so this is the performance after they destroy the information of the other data points. So this means that you want to make a predictions. These are your labels. This is, let's say, your test point. Those ones you completely shuffle the features. So there is, and everything. So there is essentially nothing useful there. So now you make a test prediction, and this is how much the test performance changes when all the other inputs are predicted or not. And most of the times it's essentially 0. So this is 1%, 2%, 1%. And for breast cancer, it was even 0%. It's more, it's a bigger difference when you make a regression, but for classification tasks, the effect honestly was marginal. And I have some assumptions here. They mentioned at some point that this algorithm learns to look essentially at the closest point into the space, basically on L2. So if you look into the vector space of the inputs, then you get to look to the closest one. This is what this algorithm learns to do qualitatively. And all those classification tasks, they have, let's say, relatively few classes. So they are either binary or they're multi-class, but with a few classes. So when you have a classification problem, you can permit yourself to do errors because you'll pick just the highest class. So for example, if you make a prediction, there is no difference between predicting 70% for class 1 or 55% for class 1, because at the end of the day, you'll just take max. So there is room for error into this thing. And the algorithm just seems to make relatively little error for classification. Like the margin of error is higher than how much information it gets from the other data points. But for regression, you need exact values. So there is not, space for having errors that are going to be amortized after that. So you get more errors. And the last experiment is that it's the one that I discussed. So they're saying that this model, it learns to rely on similar data points in the real data. They are essentially showing the attention weights on which data points it's attending. So if you look at them, this is where the important, things attend. They sorted those things based on the distance. So similar points are close into the space, and you can see that similar points attend to nearby points, because this part represents the nearby points. So essentially, this model learns to look at the L2 between data points. And it makes sense, because here it learns to look at the L2 between data points. And in this experiment, it was learning a lookup table. So a lookup table, you are essentially looking, hey, what's the closest in the input that's similar to my test point, and you look at the closest one and you copy that thing. So this algorithm is learning L2 distances, and this is a clear limitation of it, because L2 distances are just not useful when you go to high-level features. All those data sets have like 10, 50 max features. So they are, let's say, small features, small dimensional data sets where you have where the L2 distance is meaningful, but when you go high dimensional, it's not meaningful. And this is the paper, and they're inviting you to work on it, meaning they are showing some, in a way, obvious limitations of it, because they use the standard attention mechanism. So it doesn't scale well and all those things, and there is plenty of work in Gaussian processes and in transformers, which essentially learn to approximate the attention matrix. And you can use like a lot of stuff. You can use essentially inducing points, kernelization, sparsity methods, all those things. I invite you to read the paper, and I checked the appendix. It's like 25 pages, and honestly, I'm like super surprised of the quality of this publication, because they clearly have put a lot of time into it. And just like if you read it, and if you read the appendix, it's a lot of effort put into it. So execution is great, idea is interesting. I'm a bit skeptical that it's going to scale well to high dimensional data sets, but I guess there's place for future research. Thanks so much for watching, and see you in the next one.